Welcome to the fourth part of the series of lecture related to the RM software for filter design. This part will be devoted to the Chebyshev type 1 or polynomial Chebyshev filters and a modified set of Chebyshev characteristics, while at the end some comparison between monotonic and non-monotonic amplitude characteristic of polynomial filters will be given. Here is the content of this lecture. First, the Chebyshev type 1 will be introduced, then the modified Chebyshev, which is unique property of the RM software, will be introduced. Then a comparison will be done between Chebyshev type 1 and the modified Chebyshev ones. We will pay some attention to the group delay response of the Chebyshev type 1 filter. And finally, we will compare it with its monotonic counterparts. The most popular non-monotonic amplitude characteristic is the one exhibiting equi-ripple amplitude in the passband. Since it is obtained by the use of Chebyshev polynomials for creation of the characteristic function of the filter, it was named Chebyshev. And since there is another one where the Chebyshev polynomial is used in the denominator of the characteristic function, this one is called Chebyshev type 1 filter. The main property of this class of filters is that for a given variation of the amplitude in the passband, this characteristic exhibits the largest selectivity, the most selective filters of all. Since the passband attenuation touches the abscissa minimum number of times, one may state that this class of filters has all its attenuation zeros distinct and laying on the axis of real frequencies. Here is one example where the attenuation characteristic of a seventh order polynomial Chebyshev type 1 low-pass filter having 1 decibel of attenuation, maximum attenuation in the passband is depicted. On this picture, the passband is presented with linear scale, while the stopband, it is only a skewed line, is represented in logarithmic scale. You may read log of omega at this part of the drawing. It is important to mention that for even order Chebyshev type 1 filters, the amplitude characteristic does not start with unity gain. In fact, the gain at the origin equals the gain at the cutoff frequency. In passive realizations, that would lead to different values of the source and load resistance. To avoid this, the RM software provides for the gain to start at the unity for a price of slight reduction of the selectivity. If this option is used, for example, the 16th order filter will have an amplitude as depicted here. If we pay some attention to this characteristic, we may see that the attenuation at the origin is equal to 0, which is opposed to the original even order Chebyshev type 1 filter. It will exhibit slightly smaller selectivity than the normal filter, while still more selective than its 15th order counterpart. The comparison depicted here is for 8th and 7th order filters, which means there is number 1 is 8th order Chebyshev type 1 filter, number 3 is 8th order modified Chebyshev type 1 filter, and number 2 is 7th order Chebyshev type 1 filter. As can be seen, number 2 and number 3 are starting from the origin, while number 3 has its attenuation in the stop band very similar to the one at the of the number 1. So practically this is the difference between the red and the black line is the loss which is to be paid for the advantage of having equal resistors. A specific aspect of designing selective filters is their group delay. Here, the group delay characteristic of the 7th order Chebyshev type 1 filter is depicted. As can be seen, strong distortions may be observed even deep in the passband. Note, since the area under the group delay curve is equal to n multiplied by pi divided by 2, which is in this case approximately 11, one would expect for the ideal group delay characteristic, which is the constant group delay, to be approximately 11 seconds. In fact, it is approximately twice as small. To compensate for the group delay nonlinearities, one is to add an all-pass corrector whose group delay occupies the area as depicted with the dashed line rectangle in the figure. That means that approximately one will need a 6th order corrector, which in most realizations is much more complicated as circuit than the filter itself. In the next we will observe the differences or comparisons between the Chebyshev filter and the monotonic CMAC filters. As one can see, for the stop band characteristic, the Chebyshev filter, denoted by C, is by far the most selective one, while the rest is known already from lecture 3. That, of course, is a consequence of the strong distortions or strong inserted loss in the passband by the Chebyshev filters, which, as one can see here, is totally unacceptable from application point of view. There are 3 big lobes of 3 dBs in the passband, which is a serious distortion of the signal compared. So, if one wants to transmit or receive signals with small distortions in the passband, something like the LSM filters, then one must reduce the passband maximum passband attenuation of the Chebyshev filter, which will have as a consequence drastic reduction of the selectivity. Here is a comparison of the phase characteristics of the Chebyshev and the CMAC filters. The characteristic is at the origin shifted by pi to make it more tractable. As it is in general, it is not easy to capture the properties of the filter by simply looking at the phase characteristic, but nevertheless one can see that the Butterworth filters have a much more linear characteristic than any other, and that the Chebyshev filters have the most nonlinear phase characteristic. That is mapped into the group delay characteristic, and we can see that the Chebyshev, as already shown, filters have dramatic change of the group delay in the passband, while the monotonic ones may be considered advantages, especially the LSM, which is much more selective than the Butterworth, which has a much smaller, incomparably smaller attenuation in the passband than any one of the rest of the classes, and of course it has an acceptable selectivity which is larger than the Butterworth one. Here a comparison is made in the time domain. Here the step response is depicted, and a property which may be extracted here is that the less selective filters have the smallest rise time and the smallest delay time, but they have not the smallest overshoot and undershoot, while the most selective filters have the largest delay time, the largest rise time, and have the largest undershoot, which is in this case really large. So when we look at the Chebyshev characteristic, we can see that it has a very large undershoot, but not much smaller overshoot than the rest of the characteristics. Similarly, when we look to the Dirac or pulse response, we are getting that the Butterworth filter has a smallest delay, has largest main lobe, which is preferable for time domain applications, while the Chebyshev filter on the other end, of quality, has second smallest lobe and largest undershoot of all counterparts. At the end, we have here a diagram which represents the derivative of the characteristic function of two filters or two solutions, namely of the Halpern and the Chebyshev. One should have in mind that the Halpern solution has the largest derivative in the passband as compared with the rest of the monotonic filters, so it is any other monotonic filter will have smaller changes of the derivative of the characteristic function in the passband than the Halpern, and will be even better. Why is the filter which has small variation of the derivative of the characteristic function or the attenuation in the passband better than the others? It comes from the theoretical solution that says that the sensitivity or the increment of the attenuation as a consequence of variation of a circuit parameter is proportional to the derivative of the characteristic function. So the larger the derivative of the characteristic function for a given frequency, the larger the mapping of the increment of the parameter into an increment of the attenuation. As we can see, from that point of view, Chebyshev filters are suffering of serious disadvantage. That would be the end of the part 4 of the series of lectures. Thank you for your attention.